Okay, guys, just like with vision, I'm going to give you a brief overview of hearing, but pay attention because I'm going to give you some of the highlights that you're going to need to know for the AP exam. Oh, and hello! So first you have your sense of hearing, which is called audition. And you'll notice that the types of waves for audition look different than the types of waves for vision. For vision, you're using sine waves or transverse waves, and you'll recognize those waves over here in this area. For hearing, you have longitudinal waves, and those waves look like this up here. To explain longitudinal waves, we have Miguel.
So the main difference between a longitudinal wave and a transverse wave is in what the particles are doing. So in transverse waves, the particles vibrate perpendicular to the direction the wave is moving. In a longitudinal wave, the particles vibrate back and forth in the same direction that the wave is moving. So what this diagram here represents is it's a model for what the molecules of gas are doing in air as the longitudinal wave travels. You'll see that there are areas over here where you have these lines that are close together. They represent high molecule density or gas molecule density. So we call this a compression, and it's kind of similar to a crest. There are areas that have very low density, and those are similar to troughs. So the distance from a compression to a compression, in this case here, this is the wavelength. So this is a wavelength, this is another wavelength here. You'll see two wavelengths here, almost three wavelengths. The other thing that we need to talk about when it comes to waves is frequency. So we know that frequency of visible light we detect as color, well, the frequency of sound we detect as pitch. So low pitch sound is a very deep, a very bassy type of sound, and the human ear can resolve about 20 hertz. That's your lower end for hearing. So anything lower than 20 hertz you won't be able to hear. Actually, it's called infrasound. The upper end of hearing is 20,000 hertz. It's a very high pitched sound, and older adults probably are not able to resolve that high pitched sound. In fact, there are sound generators that you can access online and generate these sounds, and your parents may not even be able to hear them. So the range of hearing is 20 hertz to 20,000 hertz for humans. If you take the wavelength and the frequency of sound and you multiply them together, you get the speed of sound in air, which is roughly around 340 meters per second, and it's dependent upon temperature. The other thing we need to talk about is amplitude. So we know that the amplitude of light we detect as brightness. Well, the amplitude of sound is volume or loudness. It's hard to really talk about amplitude in this diagram here. So if you have very high amplitude sound, you'll see these compressions are like really squished and the expansions are kind of really spaced apart. But another way of talking about amplitude is to think about sound level. So you may have heard of decibels, and you may have heard, like, if you have a sound that is 100 decibels, that's a really loud sound. It's fairly complex. It's based on a logarithmic scale, and the lowest decibel level that you can have is 0, and you can't even hear that. So you might think that 40 decibels is really loud, and it's really not. It would be akin to kind of like a whisper. 75 decibels is probably what you're listening to right now as you're watching this screencast. 100 decibel things are starting to get kind of loud. So 100 decibels, 110 decibels might be like a leaf blower. 120, 130, you're probably looking at like a concert or a jet engine. And then once you hit 140, things really start to literally hurt. And then 150 and 160, you will be in pain. So that's it. We've talked about wavelength, frequency, speed of the wave. We've talked about amplitude, and that's it.
The last little bit here really is your timbre, and your timbre is essentially saying that like there's a quality to the sound that you're hearing that's different. So if Miguel and I were to speak at the same pitch and the same volume, you'd probably be able to tell our voices apart no problem. And that really is telling you that like there's a quality of the sound. Like you could tell a trumpet and a clarinet apart playing at the same volume, same pitch. Basically because sound is actually pretty complicated. Oh, and I should say here, so there's no confusion, that timbre is spelled Timbre. So breaking down basically what you need to know, let's start with this. Your ear is essentially divided into three parts. Your outer ear, which is responsible for air conduction, your middle ear, which is essentially responsible for bone conduction, and your inner ear, which is essentially responsible for fluid conduction. I get that air and fluid, air is a type of fluid, but perhaps liquid would have been a better word, but there you have it. Air conduction, bone conduction, fluid conduction, and you're going to want to remember that. So starting with your outer ear, you have your pinna, which is really what you think of as this entire part that you can see. So if you were to tell me that you think I have big ears, you're basically telling me that I have big pinnas. And actually, having the big pinnas would be sort of an advantage in terms of hearing things. Because the job of the pinna is to take that the sound waves that are coming through and help to focus it towards the auditory canal. The next structure is your auditory canal, and your auditory canal is this tube-like structure that's going to help focus the sound towards the eardrum or your tympanic membrane. So these longitudinal waves that are coming through and being focused in your outer ear via your pinna and then your auditory canal will ultimately cause the tympanic membrane to vibrate right there and will be the start of the bone conduction that happens in your middle ear. So if you consider that the job of the outer ear was to gather and deliver sound waves to the middle ear, then you want to think that the middle ear's job is to amplify and concentrate the sound from the outer ear to the inner ear. So that tympanic membrane, or as you know it as the eardrum, is this thin, tightly stretched membrane at the end of the auditory canal that it's vibrating is essentially going to start that bone conduction. It's going to cause the ossicles to vibrate. Now the ossicles are these three bones here, the malleus, incus, and stapes, also known as the hammer, anvil, and stirrup. They're the three smallest bones in your body. The malleus is going to hit into the incus into the stapes, and the stapes is going to hit into the oval window, which is the thing that's vibration is going to cause the vibrations to start in the inner ear. So it's going to start the process of fluid conduction. Now, as we start the inner ear, let me remind you, the outer ear, that air conduction, is to gather and deliver sound waves to the middle ear. The middle ear is bone conduction, and its job is to amplify and concentrate the sound from the outer ear to the inner ear. And the job of the inner ear is to take that information and transduce it into neural impulses to be understood by the brain. So when the oval window vibrates and causes fluid conduction in your inner ear, it's causing fluid conduction in your cochlea, which is this sort of snail-shaped structure in your inner ear right there. That's your cochlea. Your cochlea has two things that you need to know. It's obviously more complicated than that, but two things that you need to know. And that is that it contains the basilar membrane and the organ of Corti. The organ of Corti inside your cochlea has hair cells that are going to be responsible for transducing ultimately information to your auditory nerve. And that's the pretty simplified version. I'm going to explain both structures, but in the AP exam or on the AP exam in the past, I have seen them reference the basilar membrane, actually even in short answers, more so than the organ of Corti. So looking at this picture here, which is basically what I was describing, just simplified as taking out any extraneous information. You have your outer ear where you have air conduction, middle ear bone conduction, inner ear fluid conduction. And I want you to focus then on the inner ear part, the cochlea. And what I want you to see is that they've taken the cochlea here in this image and they've uncoiled it to some extent. which is really helpful in seeing what happens here. So your cochlea is filled with different types of fluid. And also in your cochlea, you have that basilar membrane. And the basilar membrane is interesting because if you were to look at essentially the first parts that would start vibrating after the oval window started vibrating, you would have the area of the basilar membrane that responds best to the lowest sounds. And as you move in this direction here, as you move in this direction this way, you're going to move towards the area of the basilar membrane that is going to be maximally responding to higher pitch sounds. So lower pitch sounds at the beginning, higher pitch sounds at the end. So if you think of this sort of stretched out, this basilar membrane stretched out, you'll note that as the waves caused by the oval window that's going to start the fluid conduction, these will cause the waves in the basilar membrane to start moving, and the height of those waves are going to hit its maximum in and around the spot on the basilar membrane that's most responsive to the frequency of the initial stimulus. So in this way, the basilar membrane is going to be able to accurately translate the frequency of sounds picked up by the ear to neural impulses to the brain. Now, the translation of that movement in the basilar membrane there is going to be done by the organ of Corti. This is essentially the receptor organ of your ear that sits atop the basilar membrane. And your organ of Corti contains hair cells. And hair cells are so named because they have these like hair-like protrusions from the end of the cell called stereocilia that are going to bend in response to the movement of the waves in the basilar membrane. The movement of these stereocilia will cause, or these hair cells, as you should know them, will cause ion channels to open and the release of neurotransmitters. Long story short, it's ultimately going to help us send information or transduce information, auditory information, from the sound of the initial stimulus to something that we can perceive in the brain. Remember that it will end up ultimately going to that auditory cortex in the temporal lobe. It gets routed through the thalamus, though, like all senses except for olfaction. So this place theory basically describes what I was just saying about the basilar membrane. So it's a theory that explains how we hear high-pitched sounds. So we hear high-pitched sounds corresponding to the place along the basilar membrane that is most stimulated. And if you look at this image, it tells you what levels you can detect and on which area of your cochlea you can detect it, or your basilar membrane you can detect it, which is inside your cochlea. This theory works better in explaining how we hear high-pitched sounds, not really low-pitched sounds, having to do with how frequent neurons are actually able to fire. The frequency theory is a theory explaining how we hear low-pitched sounds. So again, you have the hair cells in the basilar membrane, or really on the organ of Corti, that are going to bend and fire neural impulses, action potentials, right, at the same rate as the sound frequency. This theory is going to basically work with the volley principle. It's basically saying that, like, because there's a maximum amount of neurons that are going to be working here, and there's a maximum rate of responding, that their experience of a pitch is going to happen between alternating firing of groups of neurons along the membrane. But if you think of it like this, a frequency of 90 hertz would produce 90 action potentials per second in the auditory nerve. And you see where this would become a problem with the highest frequencies. So conduction deafness is middle ear deafness. And this is a problem with transferring sounds from the outer ear to the inner ear. So it's a problem there in the middle ear. And in this particular area, since the job of the middle ear, that bone conduction, is for amplification, the problems here would be solved by using a hearing aid or replacing one of your ossicles. Nerve deafness is a problem really with the inner ear. So damage to hair cells, your cochlea, or your auditory nerve would cause nerve deafness. Things that could cause that would be diseases, aging, loud noise. We already mentioned going to concerts that are really loud can over time cause permanent hearing loss, which is why you want to protect your ears when you go to concerts by wearing earplugs. Just the act of getting older will cause you to lose some ability to hear, particularly the highest pitch sounds. So I don't know if you've noticed somebody whose hearing has started to go as a result of aging, or otherwise, but for some reason they've experienced some nerve deafness. They are not hearing higher pitch sounds, so like they're more likely to respond to male voices. Although being clear and articulate, really enunciating your words, and looking at the person you're speaking to will all help with that. The damage with nerve deafness is almost always irreversible. In some cases, people can get a cochlear implant. So a cochlear implant is that small electronic device used to treat nerve deafness. It can be used so long as the auditory nerve is intact. If the auditory nerve itself is damaged, you're not going to be able to, the cochlear implant's not going to help you at all. But the job of the cochlear implant is to bypass the hair cells in the organ of Corti and directly stimulate the auditory nerve. You should also know that the use of a cochlear implant is kind of controversial in the deaf community. If you know anybody who is deaf, you'll notice that people in the deaf community largely do not view deafness as being a disability. And the fact that there are so many treatments for deafness now mean that the size of the deaf community is shrinking. And so if you're deaf, then so is the world of people that you can communicate with without any issue at all. And I would say that if you are communicating with somebody who's deaf and you do not speak sign language, that you make sure you do a couple things. One, look the person that you're talking to in the eyes. It sounds strange, but so many people, if they're deaf and they have an interpreter, a lot of times in communication, people talk to the interpreter instead of the deaf person, and they kind of get cut out of their own social interactions. So look them in the eyes, use hand gestures, and context clues, that sort of thing will help. And the other thing you want to know is that if a deaf person were to get a cochlear implant, they would get this crude approximation of hearing, and now they're dealing with the sensation of it, but not the perception of it. So where if you're hearing, you have learned what different sounds mean and what you need to orient to and that sort of thing. A deaf person at whatever age they get this cochlear implant will very frequently be getting that information for the first time, and it will initially be rather confusing.